Static language models break down when they encounter novel edge cases. When an environment changes unpredictably, rigid, pre-programmed execution sequences simply seize up. To solve this, developers try giving agents the ability to rewrite their code on the fly. But these ad hoc solutions entangle the agent's decision-making logic directly with its underlying tools. When an agent mutates its state without strict boundaries, a single hallucinated line cascades through the entire system, leading to irrecoverable runtime crashes. Right now, these updates rely entirely on brittle glue code. Developers are forced to patch disparate components together without any formalized safety interfaces. Modifying a tightly coupled monolithic codebase prevents an agent from ever achieving safe, sustained adaptation. The industry has built standards to help agents communicate. Protocols like Anthropic's Model Context Protocol and Google's Agent-to-Agent framework allow models to invoke tools reliably. But an invocation protocol is different from a state mutation protocol. Routing data between a static model and a static tool is a simple connectivity problem. Safely altering the internal structures of those tools and tracking those changes across multiple versions is a completely separate engineering challenge. Without native support for component life cycles and strict version lineage, an optimizing agent is flying blind. It cannot safely iterate because it cannot identify what changed, and it cannot reverse a broken update. The Autogenesis protocol, or AGP, is designed to bridge this gap by strictly decoupling the evolutionary substrate, what changes, from the evolutionary logic, how it changes. To build truly autonomous systems, self-modification must move out of the realm of ad hoc software engineering and into a standardized two-layer protocol framework. Layer 1 is the Resource Substrate Protocol Layer. This layer deconstructs the agent. It takes internal system components and isolates them into passive, independently managed entities. Every instance of a prompt, tool, or memory block is assigned an explicit registration record. This defines its state, metadata, and lifecycle interface. When updated, the protocol increments its semantic versioning identifier, creating a permanent, auditable lineage. Crucially, these entities encapsulate zero optimization logic themselves. They are strictly passive targets for external manipulation. By externalizing these components as version-tracked resources, the agent's core reasoning logic is permanently insulated from execution failures on specific tasks. To optimize these disparate resources, the protocol uses a mathematical projection called variable lifting. This operation takes wildly different formats and homogenizes them into a single targetable topological space. Once flattened, the system applies a binary learnability mask, assigning a 0 or 1 to specific nodes. This mathematically delineates the trainable parameter subspace, dictating exactly which elements the optimizer is authorized to modify and which remain fixed. Variable lifting takes tangled, chaotic system code and transforms it into a rigorous, control-theoretic surface ready for formal algorithmic manipulation. This manipulation happens in Layer 2, the Self-Evolution Protocol Layer. This is a strictly typed operator algebra governing state transitions over the newly flattened variable space. The cycle begins with the reflect operator, mapping raw execution traces to causal failure hypotheses. Next, the select operator acts as the generative policy, translating those hypotheses into concrete modification primitives across the learnable subspace. The improve operator then executes the physical state transition via standardized APIs, yielding a provisional candidate state. Before going live, the evaluate operator tests that candidate against strict safety invariance. Finally, the commit operator governs the final transition. It rejects degrading updates to trigger a clean rollback, or it accepts improvements to write a permanent versioned change. Because this operator interface is entirely mathematical, the execution engine does not care which optimizer you use. The exact same loop runs inference time textgrad, GRPO, or reinforce++ algorithms without requiring any structural architectural changes to the agent. The protocol converts heuristic, text-based code editing into a mathematically bounded, monotonically improving closed-loop control process. In practice, this protocol deploys as the Autogenesis system, utilizing a decentralized agent bus architecture. A central data spine routes message packets between specialized submodules like an orchestrator, a tool generator, and a deep researcher. Upon receiving a task, the orchestrator generates a structural execution graph, a plan document, to break the problem into independent steps. This coordination structure is itself registered as a version-controlled resource on the substrate layer. This makes the system's own planning logic intrinsically evolvable. The subagents then execute concurrently. The message bus decouples task dispatch from task completion, removing the synchronization overhead that usually throttles multi-agent networks. If a tool generator subagent encounters an unexpected environmental error while running a novel script, it independently triggers the evolution loop. It reflects on the error trace, rewrites the tool script, and verifies the candidate locally. Once the commit operator records the updated tool version to the global registry, that new capability becomes instantly callable by every other concurrent subagent on the bus. Integrating self-evolution directly into the coordination loop allows for expanding network capabilities without requiring global system freezes or manual intervention. On the Gaia Level 3 benchmark, a baseline static agent plateaus near 60%, while Autogenesis reaches 81.63%. That's a 33% relative gain on the hardest tasks, because the evolution loop dynamically refines novel toolchains that static kits lack. Unlike traditional reinforcement learning, the system achieves this adaptation entirely at inference time, avoiding the massive computational cost of updating model weights. Software engineering for AI is moving beyond the limitations of optimizing textual prompts. We are now standardizing the architecture of adaptation itself. This represents a transition from manual prompt design toward the formal engineering of self-modification protocols. By establishing an auditable, rollback-supported mechanism for state mutation, Autogenesis provides a structure for agentic systems to reliably learn from and adapt to their environments.